Hello there, welcome to 2.7 Part 2. My name is Gregory Carlson. Let's do a few more of these graphs and do these shifts. So the next one is y equals 1/3 times x to the 3. So we know what the parent function of x to the 3 looks like, so how would we do this on it, 1/3? Well, remember, when we multiply by a fraction, it takes the graph longer to get bigger, so it makes it wider. It's kind of a horizontal shift. So what you want to do here is notice we're still going to go through 0, 0, so let's put that point in. Now you want to if we go over 1, instead of going up 1, we're only going up 1/3. So it's over 1, up 1/3, over 1, down 1/3, but that's kind of hard to graph. So instead you should be deliberate about what point you plug in here for x to get a point. So don't plug in 2, because that won't eliminate the fraction, but we could plug in 3. Because if we plugged in 3, it'd be 3 times 3 times 3, which is 27. And then 27 divided by 3 is 9. One of the 3's cancel. So if I plug in the point 3 for x, I'll get the point 9 for y. Because 3 times 3 times 3 is 27, times 1/3. 27 divided by 3 is 9. So if I plug in 3, I go up 9. And that at least gives me a concrete point I can put in the graph. And if we go to the left 3, -3, it'll be -9. So the graph will kind of look like this. And you can see that that's wider. It's hard to tell, but you can see that that'll be wider than the regular graph, which was skinnier, kind of went like that. So there we go. Let's graph the next one. Y equals the square root of x minus 4 plus 2. Here's where you really need to know what your parent functions look like. Let's start with this minus 4. This shift is inside the square root, so that means it's going to move us 4 to the positive side. So 1, 2, 3, 4. Next, I have this plus 2, which is going to bump us up 2 spaces. So it's going to be 1, 2, 3, 4, 1, 2. So that's where our graph is going to start, right there at the point 4, 2. Notice the domain of this is not going to include any of these positive points, because like if I plugged in 3, for example, I'd get 3 minus 4, which is -1, and we'd have a negative in the square root. So subtracting 4 has shifted my domain this way 4 spaces, because we can't get negatives in the square root. All right, once you're here, it's just a regular square root graph. The square root of 1 is 1. Then the square root of 4 is 2. So you go over 4 up 2. The next one would be over 9 up 3, and then over 16 up 4. You see how the square root works. So there's your square root graph. It's the same as the parent function. It's just been shifted over 4 and up 2. Let's graph this one. Y equals -2 times x minus 3 to the 3 plus 6. So we shifted 3 to the positive in this direction, and then 6 going up. So 1, 2, 3, 1, 2, 3, 4, 5, 6. Drop a point right there. All right, normally for a cube, we would go over and up and to the left and down, but because of this negative, it flips it. So I'm going to go this way and up, and because it's a 2, it's made it more narrow as well. So make sure you keep all of those effects together. It's going to be over 1, up 2 like this, over 1, down 2 like that. Next, we would go over 2, down 8 normally, but because of the 2 there, it would be over 2, down 16. 8 times 2 is 16. So 1, 2, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 right there. So you can see that there's our point right there, and up like that. So that's more narrow than a regular cubic function because we multiplied it by 2. And also notice, normally the cubic function goes like this, but because of that negative, we flip it, and so it's going to go up and down like that. 3 more to go. Y equals 1/2 times x plus 1 squared plus 4. So it's a square, so that's a quadratic function, which you should know from your page 25. So it's going to be -1 and then up 4. So we move to the -1, change the sign, move to the left one, and then up 4. There's our vertex. If that half wasn't there, we'd be done. We could just write a parabola. But because of the half right there, we need to multiply all of our parabola points by a half. So instead of going over 1, up 1, it'll be over 1, up a half. Instead of going over 2, up 4, we multiply that by a half, so it's over 2, up 2. Over 2, up 2. Then it would be over 3, up 4.5, because normally we'd go over 3, up 9, but we have to divide that 9 by 2. But we've already got a few points, so I think we're okay. It's opening up because it's positive. So there's your graph. How about this one? Y equals -x squared minus 2. We're not moving left or right at all, but we are moving down 2 spaces. It's a regular x squared, except it's negative, so it's going to open down. So over 1, down 1. From the vertex, over 1, down 1. Over 2, down 4. Over 2, down 4. And if you wanted, over 3, down 9. Over 3, down 9. And every time I go over, I'm going over from the vertex. So connect those dots and you're done. Last one to do on this. Y equals -3 times x minus 4 squared plus 6. Why don't you pause the video and try to do it on your own, and then I'll show you the answer in a few seconds. So see if you can get it on your own really fast. Okie dokie, hopefully you paused the video and got the right answer. So here we go. It's +4, +6. So 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. There's our vertex. Remember, we flip the sign when we're moving left and right. Then we're opening down, and it's multiplied by 3. So that's going to make it open down and get very narrow. So normally we would go over 1, down 1, but instead we times it by 3. So it's over 1, down 3. So over 1, 1, 2, 3. Over 1, down 3. Normally we'd go over 2, down 4, but now we're going to go over 2, down 12, because 4 times 3 is 12. So 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Same here. So there's your parabola that's opening down, that's very skinny. So you will get these with practice. If you don't understand how to graph the parent graphs, we're going to practice those in class. But after you know how to make the parent graph, it's just a matter of applying these shifts. Okay, let's talk about symmetry here for a second. One of the things that can happen with graphs is symmetry. So we say that a function is even if it's symmetrical to the y-axis. So I'm going to grab page 25 for a second. Let's see which functions were even. They're even if they're symmetrical to the y-axis. So this one is an even function. See, it's like a mirror image of itself going left and right. This one is not even because it's just not. This one mirrors image itself. Here's another one that's even. Do you see how it matches itself on left and right, as if I just cut a line right down the middle of it? Let's see, are there any other even graphs? Oh, here's an even one. It's matching itself on the left and the right. And this graph is even because it matches itself on the left and the right. So notice, by the way, that x squared is even. Also, x to the 4 is even, x to the 6, and so on. So if it has an even exponent, then it's probably an even graph. Not always, but probably. The way you would write that with your equation is if you plug in a -x, it equals the same thing as when you plug in that positive x. And that should make sense to you. If I plug in 2 and get a value, and -2, I should get that same value, which in this case would be 4. So that's important. So when you plug in x, you get a value. When you plug in a negative, you get the same value. If that's true for the entire graph, then that means it's even. So here's how to check it. We'll do these 4, and then we'll call it a day for part 2. The way you check to see if an equation is even, if it's symmetrical to the x-axis, is for every x, you plug in a -x. And if it equals the same thing as what you started with, you know you're good to go. So let's plug in a negative x every time I see an x. And you'll see that because we have a negative inside that square, when we square it, that negative goes away. So you see that these two are the same. When we plugged in a negative x, it simplified to the same thing we had. So that means this first graph is even. Let's see if this one is even. I'll plug in a negative sign for x. I'll replace x with negative x. This doesn't simplify. The negative sticks around because the odd doesn't cancel it. Negative times negative times negative is, is still negative. So this will be negative x to the 3 plus 5 equals y squared. So this one's not even. We can't say that it's odd. It's just not even. How about this one? Is this one even? Plug in a negative. We see that this 4, that's going to cancel out that negative sign because 4 negatives make a positive. This negative x will get canceled because of the square, minus 10. And you can see that these two graphs are the same. So when we plugged in a negative x, all of these even exponents took care of it. So this third one is even. And this fourth one, if we plug in a negative x into the absolute value of a negative sign is just positive. So we see that this one is even as well. So that's how to check if something is even by just plugging in into the equation. Plug in negative x for every x. And if it simplifies, like because it has even exponents or an absolute value, and if the final equation matches the initial one, then you know that it's even. Otherwise, it's not even. I'm way over on time, so I will see you in part 3.